Episode 3. What is a subnet mask? In the previous episode, we looked at what an IP address is. As a reminder, it is 32 bits long, 4 octets, and takes the following forms in decimal and binary notation. We can run through a quick example. Using the table, we set the bits to 1, which equal the decimal value. The example being decimal 172.16.25.197. So, what is a subnet mask? First, we need to ask a question. What is a layer 3 network? Imagine for a moment everyone in the country lived in one massive, sprawling city. The congestion, when people tried to get anywhere, would cause havoc, and the noise would be deafening. Now, imagine far less people living in different places with motorways connecting them. The signposts are the routes. They tell us which way. The four-ways or crossroads are the routers. They provide a way to get there. This, in very basic terms, is the difference between a layer 2 network, the one huge sprawling city, and a layer 3 network, where there is far less noise and far less congestion. It requires a router to route traffic between the different layer 3 networks. A layer 3 network allows us to reduce noise and congestion, which makes for a more efficient network. The layer 3 network of 10.0.0.0/8, using only the first 8 bits for the network portion, can accommodate over 16 million uniquely addressable hosts. This is because the 3 octets from the right, 24 bits, can all be used for host addressing. The network portion is the first octet from the left. To represent the prefix length, network devices use a special type of IP4 address known as the subnet mask. It is made up of 32 bits, just like in the IP4 address. The subnet mask is shown by placing all ones in the network portion and all zeros in the host portion. In the case of 10.0.0.0 on a /8, the /8 represents 8 bits for the network portion. Remember, it is the higher order bits from the right that represent the network portion. So a /8 of 8 bits written as a subnet mask is 255, which is all ones, .0.0.0. At layer 3 of the OSI reference model, we break up the larger networks into smaller ones and use layer 3 routers to decide how to get the packet to its destination. As you can see, layer 3 of the OSI reference model maps to the internet layer of the Department of Defense model. I will be doing an episode dedicated to these two models. Do you remember this excerpt from RFC 791? We have covered half of the address portion, and now, with subnetting, we covered in simple terms the route. I will be, however, dedicating the next episode to layer 3 routing and the role of routers. Okay, let us briefly look at what a router is. Your computer needs to be told how to get anywhere other than the network it resides upon. In general, you have what is called a default route. This takes the form of all zeros with a next hop of the router. Now, server A has a default route of 192.168.1.254, which happens to be a layer 3 router. In order for server A to talk to server B, it has to know the next hop of how to get there. In this case, it will be server A's default route, which, as we now know, is set to 192.168.1.254. Server A's router knows about server B's network and routes the packet to server B's router. This is what routers do. They make routing decisions and forwards the packet towards the destination over what it believes to be the best route. There are three major classes of networks: Class A, B, and C. Class A is from 1 to 126, using the first octet for the network and 24 bits for hosts, which gives a default subnet mask of 255.0.0.0. Class B is from 128 to 191. It uses the first two octets, or 16 bits, for the network and 16 bits for the host portion. This gives a default subnet mask of 255.255.0.0. And finally, Class C. This ranges from 192 through to 223. It uses the first three octets, or 24 bits, for the network and the remaining 8 bits for the host portion, which gives a default subnet mask of 255.255.255.0. One important range reserved is called multicast. This is similar to a broadcast, however it is not sent to all. Instead, it is directed to a group of hosts. Remember, an IPv4 address contains the higher order bits, which define the network, and the lower order bits, which define the host range. As can be seen from the diagram, there are three distinct IP networks: 192.168.1/24, .2/24, and .3/29. The two servers' layer 3 networks use the same prefix or subnet mask of a /24. As we now know, a /24 means we are using the first 24 bits as the network portion, and it is also represented by 255.255.255.0. The first three octets are set to all ones. One server is on the 192.168.1/24 network, and the other is on the 192.168.2/24 network. All the bits in the last octet, in red, are used to address hosts on the network. The three octets from the left are used to define the network the hosts reside upon. As you can see in the table, as we increase the number of bits used in the third octet, this changes the network the host is residing upon. Note, no bits from the host portion, the last octet, are used for the network address. This is because we are using a 255.255.255.0 subnet mask, which means only 24 bits are used for the network portion, and the last octet remains for the host addressing, hence the /24. The slash denotes how many bits are to be used for the network portion. We now know what a 255 subnet.255.255.0 subnet mask looks like and what effect it has upon the IP address of a device. We have determined it provides for 254 IP addresses for the hosts, as 24 bits are used for the network portion. Now let us take a look at the third network on the diagram, the /29 prefix, or 255.255.255.248. The link between server A and server B uses a /29 prefix, or, as just mentioned, a 255.255.255.248 subnet. Looking at the diagram, we can see we have borrowed an additional 5 bits from the octet as network bits. Hence the fourth octet in the subnet mask is 248, 128 plus 64 plus 32 plus 16 plus 8. This has the following effect. It reduces the available hosts from 254 to 6, as we now only have 3 bits remaining for the host portion. It increases the number of available layer 3 networks from 1 to 32, as we have increased this by 5 bits. Each time you borrow more bits for the network, you reduce the number of hosts which can reside upon it. As you can see, the binary address remains the same. However, the subnet mask uses 5 additional bits for the network portion. Looking at this table, we can see in the last octet we do not use the host portion, the last 3 bits in red, for the network. The bits to the left of the host portion change in order to denote a new layer 3 network. Now, a little bit on the network address and broadcast address. This is denoted by either all zeros or all ones. You cannot use these two addresses for hosts as they are reserved. As you can see from the graphic, all the host bits are set to 0 for the network and set to 1 for the broadcast. A broadcast address is used to send a message to all the connected hosts that reside within a specific subnet. Let us take a look at the bits used for the private RFC 1918 networks. Remember, these are the 3 reserved networks for use in the home or business. These are termed private networks as they are not routed across the internet. Well, it is stated they are not. Some badly configured ISP routers do let some through. Now, the 10 on A/8 is a Class A subnet and uses the first 8 bits for the network portion. The 172.16 is on A/12 and uses the first 12 bits for the network portion. The 192.168.0 uses the first 24 bits for the network portion. So, how can we change the size of the private networks to help us make the best use of them? Well, we can borrow more bits from the host side to reduce the number of hosts, but increase the number of networks. This was demonstrated with the use of the /29 for the link between server A and server B. Let us take a look at VLSM, which stands for Variable Length Subnet Masking. In order to make the best use of subnets, we can make different sized ones. How do we do this? Well, we just borrow more bits for use for the network portion. We can now take the /24 and create more smaller networks. Note the third octet remains as 1. We are using the fourth octet to change our subnet address. Let us begin with a /25, where we're borrowing 1 bit from the host portion. We have a subnet mask of 255.255.255.128. You can see this is used 25 network bits, leaving 7 host bits. I have then increased each network by 1 bit, again borrowing it from the host side, all the way up to a /30, which uses 30 bits for the network portion. As each bit is used for the network portion, the available hosts reduce. By using variable length subnet masking, we can allocate IP addresses more efficiently and more effectively. Let us take a look at the following example. You are the IT professional designing and implementing a new network and have been tasked with designing a new IP network. You have been given the following details. Server and switch management requires 20 IP addresses. There are 40 finance users and there are 100 sales users. We know a /25 or 255.255.255.128 subnet mask allows for 126 hosts. We can use 192.168.1.0 on a /25 for sales. We then look at the 40 finance users. This can be accommodated with a /26 or 255.255.255.192 subnet mask, as it allows for 62 hosts. Finally, we look at the server and switch management network. This needs 20 addresses. For this, we can use a /27 or 255.255.255.224 subnet mask. What is ANDing? How do routers determine the network a device resides upon? They use the AND operator. The AND operator is a logical operator. It only returns a true if both operands are true. When a packet arrives at the router, it performs this AND operation to derive the network address the host resides upon. What have we learnt this episode? Well, subnet masks define which network we reside upon. We borrow bits from the host portion for the subnet. Routers allow different networks to talk to each other. We can vary our subnet size. We should use private RFC 1918 network addresses and use VLSM. And routers perform the AND function to derive the network address. Thank you for watching this episode. If you liked it, please give a thumbs up and share. If you would like to see more, please subscribe. You can also find me on X and TikTok with the handle @the_net_nous. Until next time.